Hello, atmospheric science students. This is Dr. John Schrage, and I am giving you a quick video here to talk to you about why moist air is less dense than dry air is. This is going to be done with using an equation that we call Avogadros law, though we aren't actually going to see the equation here at all. We're doing this because we're talking about the definition of a front. Fronts are going to be that boundary that separates two air masses, technically that have different densities. We don't normally think about it in terms of density in meteorology. Normally we kind of invoke the ideal gas law, and we say that as long as these air masses are basically the same pressure, we can say that temperature and density are just related. Cold air is more dense, warm air is less dense. And so air masses with different temperatures typically have different densities, and so the boundary between them counts as a front. And this is the context in which we learned, say, about the polar fronts. Cold fronts, warm fronts, and stationary fronts are all boundaries that separate two air masses with different temperatures. The ones that aren't polar fronts, though, are occluded fronts and dry lines. These are types of fronts that are separating air masses that are not necessarily different temperatures. This video is not about occluded fronts. We're going to talk about dry lines. Dry lines are going to be separating air masses that are basically the same temperature, basically the same pressure, but not the same humidity. We know that dry lines are apparently a type of front, and by our definition of front, that means the air masses that are being separated have different densities. So let me tell you what we're about to see. We're going to end up seeing that at the same temperature and at the same pressure, humid air is going to turn out to be less dense, and dry air is going to turn out to be more dense. This is often backward as to what people are thinking. They always think it should be the other way around. And to understand why this is going to be, you're going to need to understand what Avogadros law is. Avogadros law, which turns out actually to be sort of an equivalent statement of the ideal gas law, tells us that two samples of gas that are the same volume, the same pressure, the same temperature are going to contain the same number of molecules quite regardless of what those molecules are, in particular what those molecules weigh. Probably the best way for me to explain this to you is to just sort of do a little thought experiment here. Here are two jars. They're the same size. They have the same volume. And if we have, and we assume, let's say that these two jars are going to contain gas, and they're going to contain gas at the same temperature and the same pressure. So however many molecules are in the jar on the left, there's going to be exactly the same number of molecules in the jar on the right, as long as they are at the same temperature and the same pressure and have the same volume. It doesn't matter what those molecules are made of. I mean, right now, I'm showing them as being little pieces of clip art, and there's exactly the same number, but they're exactly the same stuff. But I could replace them with some heavier molecules. Here I'm drawing them using some little heavy weights there that say 1 ton on them. And it wouldn't change anything. There's still the same number of these molecules in the two jars, even if some of them are heavy like this. In the same sort of way, I could, on the jar on the right, I could replace some of those molecules with lighter molecules. Here I'm just sort of being silly about it and putting feathers in there. And in fact, these lighter molecules, again, if you add up the number of molecules in the jar on the left and the jar on the right, they're exactly the same. It doesn't matter that some of them are lighter. In fact, we could have the jar on the left have only heavy molecules, and we could have the jar on the right have only light molecules, and it wouldn't make a difference. Again, at the same pressure, at the same temperature, at the same volume, the two gases contain the same number of molecules. This, for example, is the basic story as to why helium balloons float. The helium balloon contains helium gas, which each individual molecule of helium is quite light. The helium balloon contains the same number of helium molecules that an air sample of the same size would contain of just air molecules, but since the air molecules are so much heavier and the helium molecules are so much lighter, that balloon has an overall weight that's less than the air around it, and therefore it floats. If we switch back to then looking at these two jars, let's forget about these kind of funny clip art molecules for a second here, and let's just fill these two jars with dry air at the same temperature and the same pressure. I tried to make this somewhat realistic by making some of the molecules nitrogen, N2, and some of them oxygen, O2. So I've got two jars here, and what I'm going to do is I'm going to take the jar on the right, and I'm going to make this moist air following Avogadros law. So I'm going to try to add water vapor. But I have to keep the same total number of molecules in here before this experiment as I had after it. So, for example, if I want to add some water vapor to the jar on the right, I have to get rid of some other molecules. Now, this is a little hard to explain how this would happen inside of a sealed jar. In the free atmosphere, this would involve the air expanding and stuff like that. But in just a simple little jar experiment, we're just going to have to think of it as we're going to replace a couple of these molecules, like nitrogen and oxygen, with water molecules, H2O. So now my jar on my right is moist air, and the jar on the left is completely dry air. Well, now let's actually get real information in here, and let's replace these nitrogen and oxygen and water molecules with their actual molecular weight. What do these molecules weigh? For example, nitrogen, N2, has a molecular weight of 28. The units aren't relevant to our current discussion or anything. So I could take all those little nitrogen molecules out and replace them with the number 28, and that is a measure of how much each of those molecules weigh. In the same sort of way, I could take these oxygen molecules out here and replace them with their molecular weight. O2 molecules have a molecular weight of about 32, so I could take those oxygen molecules out and replace them with the number 32. Finally, the molecular weight for water is 18. That surprises people. That's an awfully low number, but keep in mind it's H2O, 2 hydrogens, 1 oxygen. Hydrogens only weigh 1. The oxygen weighs 16. Together they weigh 18. So let's replace the oxygen, the water molecules in here with the number 18. Well, now check out what's happened. The dry air jar on the left and the humid air on the right still contain the same number of molecules, but notice that the humid air molecules overall weigh less. That's because we have replaced a couple of heavy dry air molecules, like nitrogen and oxygen, with light water vapor molecules. Overall, for the whole jar, the weight of the air, or the mass of the air inside of the jar, has gone down once we have made the air humid. So our core message here is that the dry air is going to be more dense than the humid air, assuming we're talking approximately the same temperature and approximately the same pressure. Now, that has a really important meteorological implication when we think about what is going to happen along a dry line. In the United States, we typically get dry lines in the south-central U.S., down by like Texas and Oklahoma. If we look at a map of the U.S., in that part of the world, we do have good sources of dry and moist air. We have a nice source region for continental tropical air masses. That would be our continental, dry, tropical, warm air masses. That would be like the deserts of Mexico and New Mexico, maybe West Texas, etc. And if we take a look at the geography of the region, we see that we also have an excellent source region for warm and moist air masses, maritime tropical or MT air masses. That's, of course, the Gulf of Mexico. Air masses that form over the Gulf of Mexico are going to be warm and moist, and these two locations are right next to each other. There's going to be a boundary between these air masses as they move, which I'm drawing here as this line, and this line is going to be an example of a dry line. The dry line is a boundary that separates dry air masses from moist air masses when they're at basically the same temperature and pressure. But we know that the two air masses are not the same density. The dry air mass is relatively heavy, the moist air mass is relatively light. That has an important implication if we try to draw ourselves a little cross-section across the front. Here I've made myself a little PowerPoint illustrated cross-section here. I'm trying to show that it's west to the left and east to the right in this PowerPoint. And you can see that because it's heavier, that CT air mass, the continental tropical one, is heavy and dense, and it is wedging its way under the maritime tropical air mass, that moist light air. That means that because that air mass, that dry air mass is so much heavier, it can go under the maritime tropical air mass, which rises to get out of its way. Well, lifting warm, moist air sounds like a recipe for thunderstorms to me. That sounds almost ideal, actually, for making a good thunderstorm. I mean, you're lifting warm, moist air. Sounds like it's going to have lots of energy available for lifting. Now, it turns out there's other reasons as well why dry lines turn out to be favorable for thunderstorms, but in particular, they're favorable for tornadic thunderstorms. The kind of lifting and the dynamics that are involved in dry lines turn out to be perfect for the development of tornadic thunderstorms. And if we take a look at a map again as to like where we're looking at on this map, as to where all these dry lines are happening, that's a part of the country we call Tornado Alley. It's a part of the country where it is particularly favorable. We know that there are lots of tornadoes in places like Texas and Oklahoma and Kansas and so on. That's because they get a relatively large number of dry lines. Okay, I hope this little quick tour of why moist air masses are less dense than dry air masses has been helpful to you. If you have any questions, please feel free to contact me. This has been Dr. John Schrage, copyright 2012.